All right, so moving on to number 12. All right, so we've decided that the two variables that we're going to be transforming are the friends and the income, and we're going to use log transformations. As a reminder, you cannot take the log of values of 0 or less. You can't take logs of negative numbers or 0. So because our friends variable has zeros, we have to add a constant to it. That way there are no 0 values. So all we're going to do is we're going to take the log of friends plus 1, basically. So to do this,
wait, let me stop. Does everybody understand what we're doing and why we're doing what you just said? Okay, just want to make sure.
All right, so we'll take our data frame and pipe it into, we'll mutate to create a new variable. In this case, we want to create our log transformed variables. And all we're going to tell it is create a variable called log friends1. And again, this is just taking the log of that friends1 variable, but we also have to add that constant. So we'll take the log of friends1 plus 1. And then after that, we'll add a comma, come to a new line, and we will take get our transformed income variable as well. So if we have our log income 3 equals the log of income 3. And so run this and make sure, cool, it runs, and we got our new variables. So now come back up here, throw in my assignment operator, and store it back into the data frame. So now in our data frame we have those couple variables.
Is there any reason to worry about those red warning messages?
No. No, don't worry about them.
And we're adding 1 just because there's like values of 0.
Yes.
So if you try to log transform, if you remember the formula for log transformation is it's essentially going to involve no, it's reflective or something. If you have any 0 values and you try to log transform, those will become missing values because you can't divide by 0.
And
go ahead.
I was just going to say, keep in mind that the constant is not always 1. In this case, it's 1 just because it's 0. But if you have a value of something that's -5 is your minimum value, then you need to add a constant of at least 5.01 to get it above that. You have to make sure your minimum value is greater than 0. All right, so now that we've created these log transformed variables, let's look back at our descriptive statistics of those two variables. So we take our data frame and we're going to pipe it in. We're going to select those two new variables, so log friends1 and log income 3, and then pipe that into our describe function.
Do you have to do parentheses after describe?
And so now when we look at our skew and kurtosis, it's looking a lot better. It's not, as skewed. And so skipping past 13, that's just asking for a verbal answer, where number 14, now it's saying to come in and graph those transformed variables. Basically, we can do the same thing, just come up here and copy and paste our code from before. Bring that down here to number 14. We'll paste that in, but then we just decide that we don't need all of these variables. All we need is log friends1 and log income 3. Open up our window so it doesn't yell at us. And now when we look at our distributions with those normal curves superimposed, it looks a lot better.
1 second. Can I see the rest of the code, please?
Yeah, is there any reason why there would be NAs for the log dot friends one once after you mutated it?
Because you have 36 missing values anyway in the original thing, so those are still going to be NA once you transform them.
Okay. When I did the mutate function and added the friends 1 plus 1, that made everything NA.
It made everything what?
Missing NA.
Check to make sure that you don't have some sort of capitalization error or something like that.
Okay.
Because if you did, then it would try to add 1 to something that doesn't exist, and so it would just output NAs.
Let us know when you've identified it. We don't want to move on.
Can I see the code for 13? Checking it? Okay. So describe them.
So the log transformation, as you can see from our graphs, has been effective at kind of making sure that everybody is more in the middle in terms of their values. As Austin said though, now the actual number is really uninterpretable. Because what does it mean to have, 3 log transformed friends? Jake, did you get it?
Not yet, but I'll figure it out.
Wanna go see if you can do it? Yeah, let's take a pause and make sure
Austin, while we're paused, can I ask a question?
Yeah, so.
Why, or did we check for outliers in this script?
No, not yet. That's outliers will come when we're looking at multivariate outliers.
Okay, sweet.
Which will be next lab in the Manova lab.
How did you, did I miss something? Did you remove the NAs before doing the log transformation, or that just wasn't an issue in running the code on 322?
No, so like asking like about having to remove NAs before here?
Yeah.
No, because what it's going to do is for every row in the data set, it's going to take friends 1, add 1, and take the log. So if there's an NA value and it adds 1, then it's still NA, and then when you take the log of it, it's still NA. And so in that particular case, you don't. It's going to just stay NA. Did you get it figured out, Jake?
Well, so at least have something in your script that's like min parentheses df $ friends 1 NA rm equals true. But that wasn't in this one. Yeah. So there's this stuff right here, and then that wasn't in up there. So I'm guessing that that's.
Oh no, that's just looking at the min and max.
Oh, okay.
Did you want to step up to this point?
So I run this right here. That's the same.
Alright, so yeah, run that line. And you got to store it back into the data.
Okay. So I reran it in the above. Okay, yes. Sorry about that.
And that min line was just to check what constant you're adding, right?
Yeah.
Quick question, well, Rose is something I can't help her with, but is there a reason we didn't use friends1.end?
No.
Should we?
Not yet, probably.
Okay.
Oh wait.
Friends 1 should be.
Yeah, I guess friends1.in. Sorry about that. On that code, that should be friends1.in, because the friends1, it'll, like those 98s or more that are still in there. No, I take that back. That's why, because in my script, I overwrote it.
Yeah, we did override it, so it doesn't.
So in yours, yes, it'd be friends1.in.
Yeah, because I did it with the point. I think you did that too.
Mine just ran just wrong.
Are we all tracking? Anybody else?
Oh wait, let me.
Did you get it? Yeah. You guys ran your script all the way up through what we had today. Yeah, you need to assign it to the data frame.
Yeah,
I just saw that.
I'm not sure why.
Oh, because right here you're saying
I have
log
it.
equals
I
instead of plus.
It's about Linux, so it's applied to Linux, so Linux is very user-friendly.
And then I printed
in its terms.
Yeah, store it back over itself.
Did he?
Yeah, she had equals instead of plus.
Oh, perfect.
Alright, so we're all good now. Any other questions?
Now we're all good?
Sweet. Alright, so then the next thing, after we look at those plots again, we want to get the correlations of our previous untransformed variable and our new ones. So you can just use the core function and tell it df friends1 and df log friends1. Sorry. And then because you have NAs, you add na.rm. Or is this one? Let's try core test. There we go. We'll use core test instead of core.
What's the difference?
There's a few, well, there's several different ways to get correlations. Core is convenient if you don't care about p-values, just because you can throw in core. If you want p-values, you have to use core test, which will also give you like your p-value and those test statistics. If you run just core, it's literally just going to output that correlation coefficient between the two. I think before in the script, if not later in the script or in the next lab, we'll use a different function called core CI that gives you confidence intervals of the correlations, gives you nice pretty plots of the correlations and stuff like that. But anyway, so core test, and when we look at the correlation between these two things, we can see we have a correlation of 0.83 essentially. And then looking at the correlation of our income variable with the log transformed income variable, again, we have a correlation of 0.84 here. So our correlations are above 0.8. So what does that tell us about this newly transformed variable?
Highly correlated with the not transformed variable.
Right. And so what does that mean for us though? That like they're correlated highly?
Put them in the analyses similarly.
Right, that they'll behave similarly in the analysis means that we're not losing a lot of information statistically by transforming it this way. If you have a low correlation, then like you might have a problem because it's not going to behave in the analysis the same way that the untransformed variable would.
And if you ever have to do a reflect before you do like reflect in square root or reflect in inverse transformation, where you're basically changing the skewness from being on the positive side or from being on the negative side to basically its mirror image, the correlations will be high, but they'll be negative. And what that means, for example, let's assume for a moment that friends was like that, and then you had to reflect before you log transformed it. You might see, for example, that lower self-esteem was associated with higher reflect transformed friends, and you might think, well, that doesn't make sense. How could kids with lower self-esteem have more friends? But it's because it's basically the mirror image of it. You have reverse coded, if you will, the friends variable. So you have to remember that interpretation, and it's why it's important to check your correlations so you remind yourself, oh, these are still basically the same variable. I can interpret the coefficients as more of this is more of that, right? Whereas if it was a negative correlation because you have to reflect, then you would have to remind yourself that what you're really looking at is lack of friends. So lack of friends was now associated with lower self-esteem. It can get really easy when you're data cleaning to kind of forget where your data are. And that's why I think it's very important to regraph it, relook at the descriptives, relook at the correlations, just so you can remind yourself, this is how I should be thinking about this variable.
You also maybe make notes or a code book or something like that.
Yeah, so, or sometimes when we've done this and I've published with it in I actually then reverse code it again And so that way when readers are picking up my manuscript and they see a negative correlation between the number of friends you have and self-esteem, instead of thinking doesn't make sense, so then I have a footnote in my table where I'm like, this variable was log transformed and reverse coded so that for ease of interpretation.
Interpretation is a great
Ease of
sentence.
interpretation.
Yes. All right, any other questions before we move on to the next piece? So the next thing we're going to do is we're going to start, so now we've gone through, we've looked at our normality, and now that we've log transformed, we're going to say all right, this is all good. We're done checking our data for normality. We're going to move on to checking for linearity of our variables. So the first thing that we are going to do is create bivariate plots of all the combinations of all our different variables. So GPA1, SMA, SRA on the x-axis, and on the y-axis, education 3, job score 3, job sat 3, one plot for each of those combinations. So first we'll just do one simple straightforward plot. So we'll start with our data and we'll pipe that into ggplot. And now when you're working with ggplot, I know most of you or some of you have done this plenty. I did post a link to a ggplot intro video, so hopefully this won't lose people to understand that now once we're working in ggplot, we're using plus signs to add new layers to the graph. So when we run ggplot, all that's going to do is initialize ggplot, and so there's a plot, but we have no layers added onto our plot. So the first thing that we want to do is, I normally add my theme first just because I like theme classic to keep it nice and clean looking. A lot of people typically add that at the end, but so now we need to add some points. It would be helpful on this graph. So we'll tell it geom point, which is just our way of saying we want the things that show up on the graph to be, dots. And now we got to give it some aesthetics. And we're going to tell it that we want our x to equal GPA1, and that we want our y to equal, say, education 3.n. Now, if we run just that as we have it so far, it's strange that it shows up white because it's gray on the screen. But anyway, so we've got some points. It's kind of hard to see because there's a lot of data in this data set. So one thing I'm going to suggest is when you have a lot of data points is to use your alpha argument as well. So here, this is not in the aesthetics because I'm not pulling from the data. I don't want the alpha, which is the transparency of your geom. I don't want it to vary based on something in the data, which is why it's not an aesthetic. So this goes outside the aesthetic. I'm just going to tell it that alpha equals, say, 0.1.
And alpha is what exactly?
The transparency. So now, all of them have transparency, and so where you see it getting darker, that's how you know that there's a lot more overlapping points at any given place.
That's so pretty.
And then for adding that line of best fit, we're just going to add another geom, and it's called geom smooth. And we'll tell it that our method equals LM.
Are we not doing lowest?
We can.
Because the smooth will actually smooth it out, whereas lowest will tell you here's how it actually looks. And I believe that for the assignment we want lowest.
I thought we wanted for each bivariate pair basically the line of best fit, the correlation between the two.
No, to test for assumptions of linearity, I think we need lowest rather than LM.
Well, then we just need...
And not smooth, I think, then.
Well, geom smooth defaults to lowest unless you tell it method equals LM, then it uses the linear regression of y on x. Although I may... Alright, so yeah. So notice how this this didn't run when I did this. And that's because here, I put my aesthetics for my x and y in my geom point, which is all great and grand, but what you put up here in the ggplot is your global aesthetic. So it's what carries through every step of the plot. So in this case, because this didn't run, all I'm going to do is I'm going to take this aesthetics and I'm going to move it up into my ggplot portion. And so now that the aesthetics are in ggplot, it's still, when you get to geome point, it's pulling those same aesthetics into your geome point. But now it's also pulling those aesthetics into your geome smooth. So now it knows, like, okay, for X and Y, like these are the things that I'm trying to create this lowest line for is based on these two variables. And when we run that, we now have our lowest line on top of that plot.
So geome smooth defaults to lowest?
Yes.
And can you tell me what the lowest line is?
So a lowest line, you can it's kind of like a localized line of best fit. So if for instance, if I change that from lowest to the line of best fit with method equals LM, like now this just gives us a predicted line for Y regressed on X.
So this is actually really helpful because I want to point out two things. Can we run both graphs? Can we run and actually there's another way to do lowest that's not smooth, that's sort of bumpy.
I mean, you can adjust the...
I think there's a different function because I ran it this weekend. It's not smooth, but maybe it's just geome
Line.
Or
Where it goes 1, 2, 3, 4.
No, not like a geome lowest.
geome line.
Well, that...
line does not.
Oh.
I just ran it. Is it path?
No, not path either. It might be something that's not an actual...
I don't know, I can find it in what I ran this weekend, but we'll just stick with smooth. Can we do two graphs then of the same variables, smooth and best fit? Because I want to answer Stephanie's question, but I also want to describe for you why we're doing it this way with the lowest line, which stands for least ordinary something squared something, I don't remember, but basically it's telling you if I wasn't forced to fit into any shape, what is the line that best describes the correlation between these two continuous variables? So you're specifically not forcing it to be straight or curved or one way or another way. You're just basically saying, show me, right? What do you want to be? And this is like, here's what I want to be. And okay, so thank you. This is perfect.
You can do them on the same plot.
So free, yeah, but for ease of interpretation for the moment, let's keep them on separate plots. This is what Austin was first describing for you, which is the linear association. It is forcing a straight line between these two variables. And it is saying if I have to force a straight line between GPA and Education 3, so this is middle school GPA, and Education 3, here's what I have. It looks pretty fucking straight. It's great. But it's always going to look straight because you forced it to be straight. Okay? When we're checking the assumption of linearity, we are not checking if I force you to be straight, are you straight? Okay? That's like conversion therapy. That's unethical.
It's illegal in some states.
It should be illegal everywhere. It's definitely unethical. This is, if I don't force you to be anything, what do you want to be? Okay? Sometimes I want to be, curved at sort of this more modest angle. Up at these higher GPAs, it's like, whoosh, I really want to be, so you can see how the line just sort of gently kind of, curves up a little bit. There's a little bit of a curve here. We didn't force it to be straight. We just said, what is the association between two continuous variables? Now, the next thing we're going to have to do is say, if I force it to be linear, is that like a serious distortion? Or am I reasonable in saying these two are basically linear? Okay? So it's the question, it's like picking out an outfit or something like jeans, fucking jeans, to try on at the store, where you're like, okay, well, here's what I naturally am, my natural size, but can I force myself to be in these, in this one? And so like sometimes you can kind of force it and it's okay, I can breathe in these, right? And other times this graph is gonna say, girlfriend, put those back. Those jeans do not belong on you.
What are the parameters that you use to understand if linearity is acceptable versus
aside from just kind of like looking at it?
Yeah, so look and test is sort of like the thing for everything that we're doing. So we're gonna eyeball, it's really good to look at your data. And then, depending on sort of like how much of a curve it looks like things have, you can then add a second, like a squared, you can run a regression, a linear regression, where you can add a squared term. So you can say, I'm gonna predict education 3 from GPA 1 plus GPA 1 squared. As soon as you add the GPA 1 squared, you are modeling a bend in the curve. You're basically saying, I'm going in this direction. Whoa.
Sorry, I just put both the lines.
Oh, okay, on the same graph. I'm going in this direction for a while, but right around here, the slope of me changes, and it now goes this way. And so if the squared term is significant, you have nonlinearity. You're significantly deviating from normal. There probably are some other tests, probably R has like a million great fun ways to do this simply. I don't know if you know of any.
Probably.
But for our purposes, we're basically gonna start with the eyeball test. And this to me, this is actually lovely to have them both on the same right now. It's like how much of a deviation at any point, and it doesn't look like these genes are gonna fit me. It's okay, right? So that's kind of how I think about this part. But there are more formal statistical methods to do that, including, like I said, just put in your, model it and see if it's significant.
When you find, if you find or know the function that does like the non-smooth line, would you be able to put it on the board?
So I have to keep up with Austin, so I'm not going to do it now, but after class, I will show you exactly what these look like, and you can rerun them with just the lowest line, which is not smooth. So that means it might look like kind of like a mountain, like I'm up here, now I'm down here, now I'm up here, now I'm down here. But the smooth is a little bit nicer in terms of, okay, overall kind of, you know, smoothing out the peaks and valleys, how do these two occur? Awesome.
So just a couple things. If you're wondering, all I did to get both the lines on one plot is I just added a new layer, and on one of them I just said geom smooth, color equals, then in quotation marks, red, red, because the default lowest line is that red one. And then I added another layer that said geom smooth, method equals LM, color equals, in quotations, blue. Now, just real briefly, as far as what's going on in the lowest curve and where that number is coming from, a way that you can conceptually think about it is, whereas this blue line is just predicting, y regressed on x for all of the data. Conceptually, you can think of a lowest line as like starting and saying like, all right, let's take these data points, and just for these, let's regress y on x and see what that slope is. Then let's shift over to these points and see what that is, and then shift to these next points. So if you have perfect linearity across this variable, that lowest line will also just be straight, because no matter where you choose some interval of x to predict, you're going to have that same thing. But if you don't have a linear relationship, let's say that once you get down towards the high end, now like it predicts a much higher value than down here. You're going to see that lowest line start curving up, because once you get here and regress y on x, it's going to give you a steeper slope. So that chunk of the line is going to be slanted more than it is down here. So that's kind of conceptually what's going on when you do these lowest curves. And
so let's do another variable together and then let the class tell us what they think. Does everybody understand kind of what we're doing at this point to check for linearity? Our models assume that variables that are continuous are linearly associated with each other, so we have to check that.
all right, so then if we wanted to look at, and again, this is just doing all these plots one at a time, so SMA. And for now, let's take off the line of best fit line. So I'm going to hash out before that plus sign of the last layer, because if not, if I just hashed out this line, it's not going to run, because when it gets to this plus sign, it's going to keep reading. It's going to ignore this and try to read down here into question 17. So just remember, but you got to put that hash in front of something like a plus sign. So now if we run this, we get our SMA education lowest line. Let's see. Anyway,
So you decided
Yeah, I
to-
think it doesn't matter, to put Lois in there, you were right, but there is a different function.
where is that? No, I did change it, actually. Just ever so slightly down at that end. But anyway, so here again, we're looking at that linearity, and again, if, like, I mean, just eyeballing that, it seems like it's a pretty linear relationship between those two. If that curve takes a significant, you know, upward slide, then you know once you get towards the higher end of math achievement, that the predictions of education is, you know, a lot more, which wouldn't be a theoretically like impossible thing to think about. Like people who are like really high in achievement, like, you know, maybe they do like have a little bit extra of a boost above people who are like moderate, and so that sort of thing. Only got about 10 minutes left, and for this portion, y'all have to, you know, copy and paste and, you know, export and save and move over and all that sort of stuff. So I'll let y'all kind of chug along working on those. And while you're doing that, I want to show you at least one thing here, and then we'll pick up on Thursday with number 17. We should be able to finish up that last little bit. We just got to run some correlations, look at missing data patterns, and then do a couple imputations. So what's up?
On the 16 it says to use transform variables.
Yeah, ignore that. That was just a vestige of copying and pasting from previous homeworks.
Yeah,
where
so I made you do a lot fewer graphs this time around than other years. So yeah, we were plotting every variable with every other variable, and now I'm just limiting it to a couple. So, thank you. So we could probably get through 17 and 18, right?
Today?
I think so.
Yeah, we can do 17, I suppose.
18 is just look at the correlations and tell me if any are problematic.
Right. I'll go ahead. I'm going to at least paste in this one piece of code and talk about it real quick. That way it'll be on the video that's posted. But so what I just want to show you here is at least one quick way of making things a little bit more simple as far as like plotting across multiple things. So what I want to do is, instead of making a graph for SMA and education, and then another graph for SMA and job score, and then a third one for SMA and whatever, is at least make them like 3 at a time, one for each, you know, X variable. So what this code here is doing is I'm taking the data frame, I'm piping it in, I'm selecting the 3 variables of interest as well as education 3, and then I have this pivot longer, and what that's doing, so if I look at just those top 2 lines, obviously it gives us our data frame down here, just as we'd expect. With this pivot longer, what I'm telling it is to take this data frame that it's giving me, and I want to change this from a wide data frame to a long data frame. And so what I want to do is, like, I'm not going to include education in this collapsing, but I'm going to change my names to xlab and the values to xval. Now let me run that, and then we'll be able to explain what exactly is going on here. So now when I run that, you'll notice I have education 3N that was excluded, minus education 3N up there. Alternatively, you could say, instead of minus education 3, it would be the exact same if you said like GPA 1 colon SRA to select which variables you are collapsing, or you can put in which variables to not collapse. So in this case, just saying don't collapse education, leave it as it is. But now I created this XLab and XVal. So for my XLab, I have GPA, SMA, SRA, and then XVal is all these. So what this is doing is taking this right here, and for this participant, it's creating 3 rows. So it'll be education, 3N is 2, and then there will be the row that says GPA, and then the XVal is 0.58. Then another row that says like XLab equals SMA, the XVal is 54. And then a third row that has SRA of 8 and makes that into the XVal. So basically just taking that, collapsing all these variables down into a long pivot table, or excuse me, a long tibble, then piping that into the same plot as before, but now I'm going to facet it by this XLab variable. And so when you run that, you can now get all 3 of those and just facet across that thing by pivoting to a long thing instead of having to copy and paste and have 9 separate chunks of ggplot code.
And just to be clear, this is just another way to do it, but if you just want to copy and paste and make the plots one at a time, that's perfectly fine.
And I'll let y'all go back to that here. We got about 5 more minutes to go over this last piece of getting these bivariate correlations. And so you could do it as you'd more or less expect with like, all right, if we're trying to get the bivariate correlations of these different things, we just select those and pipe them into core test. Then
sorry, I'm still trying to write down the code for what you just did, and I can't find it now. One second. Thank you. And so this is only doing lowest, but if we wanted to add the linear, we could add one more thing.
you just add on another layer that says
Method.
geom smooth, and method is LM.
So what's going on in the facet wrap parentheses? It's XLab dash.
That's a tilde, and then a period. So this is because you can facet by multiple things. And so if you had like xlab tilde some other variable, then it would give you columns of one and rows faceted across for the other. So by putting in the tilde period, that just says like, hey, put these in 3 columns, but don't facet it by any additional rows. If you switch that around, then it would give you, GPA, SMA, and SRA as rows across instead of columns like that. And then the scales equals free. What that does is it frees up your scale. If you didn't have that, then this GPA would also be on a 0 to 100 scale. And so this whole thing would be, crunched down and be a bunch of empty space with everything crowded down to like this much room. So that's just telling it, hey, let the scales do whatever to make the plot fit in the window as best as possible.
And so in that same, right before facet wrap, you can add one more row or one more line of code, which would be geom smooth with the method as LM. And you can change the color of that line. So you can, just like we did in the other ones, have both the best fit and the lowest line on the same graph. That way you can visually inspect, there you go, whether the linear assumptions seem to hold across these graphs. Which overall, to me, they're looking pretty good.
So once we come down here and we run, are we all good on this code up here? If not, just let me know. I can email things out and whatnot. Shoot me a message. So when we run core test, which is just one of the correlation things that you'll often see used. It basically gives us 3 separate tables in the output. Like this is the actual correlation matrix, so these are our R's. These are just our N's, and then down here, these are our P's. But that's not like, I don't like this because it's not a particularly great way to try to be like, oh, here's this correlation, now let me see what's its p-value and tracking things down, et cetera, et cetera. So instead of using core test, one thing that can be nice is to use core.ci. And it should be, oh, sorry, it's 1R. Yeah. And again, having problems because I'm too far zoomed in. There we go. So now it gives us, our nice, pretty, lower triangle. There are arguments to change to upper triangle if you want. Then down here, like you can actually get confidence intervals of your various correlations instead of just looking at p-values. Plus, one of the things that I like about it is it does give you like good, just nice, quick glance visualizations of your correlation tables. And so if you, for this line that I just ran with the core CI, let's say I save that as an object, named something. Now, whenever I run something, well, actually, let's check the structure of this something and see that it has, like, that it's this list of a lot of different things. There's row, means, SDs, TCI, PTCI, yada yada. Not going to get into what all it all means, outside of pointing out that this row, $row, is the actual correlation matrix itself. So this is what gets stored as row if you store this line. So if we call something $row, then that gives us our actual thing. And so for instance, if you write _CSV something $row, then it will output your actual correlation table to a CSV that you can go in and pull out whatever you need, copy and paste, all that sort of stuff.
Can you clarify, was that core CI that gave you the table, or was that a different function?
Both. Like core CI output this specific table. The core test put out is the one that gave us like the R's, the N's, and the P's, and then core CI puts out just the correlation table and then all of our P's and confidence intervals plus the figure.
Wait, can you show us the code for the right CSV?
Yeah, sure. So if we took this and just did write CSV something row and run that, then when I come over into my, oh, sorry, got to give it a file name, .csv. And, sorry, I stand corrected again, need to make it a data frame. And now, so all I did here is take that something $row table right here, wrap it in data frame so that it recognizes it as a data frame, and then write it as a CSV, and now .csv is in my working directory folder.
So what we're looking for in terms of multicollinearity, this is the problem when variables are too highly associated and you can't have them both in an analysis without creating problems, is any value above 0.7 might be a problem and above 0.9 is going to be a problem. So what we're checking here is we want the variables to not be so highly associated that they're kind of redundant and create problems with multicollinearity. So when answering the next question, which is just a text question, are there possible concerns? You can take a look at your table or at the graph and just see whether you have any variable associations here that you're like, probably don't want them both in the same analysis.
Can you repeat what you said about the 0.7
0.7 is where we start to worry about possible problems, and 0.9 is when we're like, too redundant, cannot have them together, period.